In this slide, we will talk about the features of Taylor series. The first feature is the conclusion of the example actually. An nth order Taylor series expansion will be exact for an nth order polynomial. We mentioned this in the previous slides for the example of Taylor series. Another feature is that for other differentiable and continuous functions, which is different from polynomials, such as exponentials, sinusoids, sinusoids, a finite number of terms will not yield an exact estimate. So for this kind of functions, which are different from polynomials and some order polynomials, and a finite number of terms never yield an exact estimate. That's why for this kind of equations, let's say, we will have improvements by increasing the order or adding some Taylor series terms, and we will have improvements, but it will never go to the exact estimate. And the Taylor series yields an exact result only if an infinite number of terms are added for these cases. So we need to separate the exact prediction of Taylor series for nth order polynomials and the exponential and sinusoids. For these kind of different functions, we need an infinite number of terms for exact solution. Otherwise, we will have just an approximation with some improvements by adding terms. In most cases, the inclusion of only a few terms will result in an approximation that is close enough to the true value for practical purposes, because we can see that the first few terms actually covers the entire prediction, and adding further later terms will improve slightly only. And the question here is that how many terms are required to get close enough? And this close enough is about the remainder term, which is the truncation error basically, and it determines this question. And this value is represented or expressed as, again, Rn. And you can see that this is in the n plus 1 degree. That's why we call this error in the degree of n plus 1. And this means the truncation error is of the order of n plus 1. This is important. Actually, there is h as well. H to the power n plus 1. This means that the error is proportional to the step size h raised to the n plus 1 power. So if we want to give an example, in a general example actually, if error is in the order of h to the n only, or h to the power n, if we halve the step size, meaning halving the step size, it's just linear, will halve the error. But in the Taylor series case, the error is, O h to the power n plus 1. In this case, halving the step size will quarter. So it has greater effect on the accuracy. That's why we actually want to use smaller step sizes to have a more accurate result to the actual polynomial, especially for the different functions than polynomials, such as exponentials and sinusoidals. So let's define an example for this and investigate the step size difference for an example. We are going to solve an example for the Taylor series with infinite terms. As we said earlier, for polynomials such as cosines, sines, or exponentials, the Taylor series doesn't give an exact result if we cut some or truncate some terms. So we will investigate this by using a cosine function, as you can see here. And for this function, we will use the Taylor series between n equals 0 to n equals 6. And we will predict the value of pi divided by 3, which is 60 degrees actually. And the value of fx and its derivatives will be found at xi equals p divided by 4. So basically the initial is p by 4 and xi plus 1 is p divided by 3. And this means the step size is always the difference of these. So it's pi divided by 12. Let's start solving this. Let's see the true function value. And we know that the true function is cosine x and for p divided by 3, let's write it in the function. Cos p divided by 3, and it gives us 0.5. So let's keep this in mind. This is the exact value, true value. And now we will use Taylor series. Let me write it down in blue. Taylor series approximation. And for that, we will use xi as p divided by 4 and xi plus 1 p divided by 3. Okay, let's start with n equals 0 because we will start with this up to 6. For this, we will only have the first term of Taylor series and it will give us an estimation. That's why we have the tilde on top of f. This is fxi for the first term. And if we put p divided by 3 as our target, it will be xi value, f p divided by 3. Sorry, divided by 4. So if, and this is the exact value, p divided by 4. This one is the exact value, so we can use that directly, cosine p divided by 4. And it gives us 0.707106781. I am using a long number, many numbers after the point because I don't want to have the round-off error to be greater than the truncation error. So I want to minimize the round-off error. That's why I'm using this much, this many numbers as the significant numbers. Now we found this, and you can see that the true value is 0.5 while the predicted value is 0.7. So we can calculate a difference between these, a true error. And this is, we will use the percentage true error. This is the real value, the true value, and this is the prediction, 0.7. And we divide this by the true value times 100%, and it gives us 41.4% error. You can see that there is a large error, so we need to increase the number of terms. So this is the truncation error actually, or because of the truncation we have this error. So that's why let's add some terms. For example, the first degree. Again, we predict xi plus 1 with the zero order term plus the first order term, and it includes the derivative times the step size h. And in here, if we write this down, fxi, we know that it is for p divided by 4, and we already calculated it as 0.707106781 over here, this one. So then we will have the derivative, and the derivative of cosine x, the derivative of this is minus sine x, sine xi. So we can just then write minus sine xi is p divided by 4 times the time step is, we said that it will be 12. So we will use pi divided by 12 over here, and the result here is 0.5219866659. And you can see if we compare with the true value over here, we are getting closer. It was first 0.7 and now it reduced to 0.5. It is very close to here. So let's calculate the error between them. And the error is again with the true value subtracted from the predicted value divided by true value times 100, and this gives us an ET of 4.4%. You can see that we reduced the error up below 5%, which is nice, but we can further reduce it by using n equals to f xi plus 1. Actually here xi plus 1 is pi divided by 3 equals fxi again plus f1, the first derivative, xih, and the second term, it is the second derivative, xi divided by 2 factorial times h square. So h is p divided by 12 always, don't forget that. And if we write this, so this, we know that this value is 0.52198669 from here. And the second, we need the second derivative. This one is actually again the derivative of this, which is minus cosine xi. So we can simply write, let me write the first term first, 198669, and then the derivative minus cosine p divided by 4 divided by 2 factorial and p over 12 square. And the result from here is 0.49774491. So you can see the error reduced further, and if we calculate the relative error epsilon t for this, true value minus approximated value 77441 divided by 0.5 times 100, we see that the error reduced to 0.44%. So 0.4% almost, or 0.5%. And you can see that adding the terms improved the error very nicely, and we can predict in a good accuracy. So we can further add up to 6 and continue on seeing how the error reduced, but we will do that in the next slide. In this slide you can see all the results for the Taylor series from order n equals 0 to n equals 6. And these are the derivatives. As you can see that the derivatives never go to 0. And that's why actually the estimate is never exact, but each added term will improve the accuracy slightly. And you can see that actually we are getting closer to 0.5, which is the exact value, but there is always a reminder term or an error because the derivative never goes to 0. So we can maybe note it as the derivative never goes to 0. This is important, and that's why we don't have an exact result. So we will never have an exact true value with finite terms by truncating. Or truncated terms. Truncated series, let's say, for this cosine function. And if we check the results or the errors, you can see that the errors are very large at the beginning. Here the book actually not using the absolute value, just using the regular error value. That's why there are negatives, but that's not really important. So we see that after the third term especially, the error reduced very well, and it is below 0.1, for example, over here, and it reduced further, as you can see, and it's almost very low, almost 0 after the sixth term. So maybe we can put a stopping criteria over here. After 10 to the power minus 5, we can stop, for example, because this is a very good prediction. Even this one is very good prediction for order of 4. And so we can easily predict with finite terms, 4 terms, for example, but it never goes to the exact value. But also you can see that most of the improvement of the prediction comes from the initial terms, and especially after the first 2 terms, it's almost 0.5. And adding more terms only slightly improve the result. And after a while, the improvement is almost negligible, especially after the third iteration, it's almost negligible. So these are the important features of the Taylor expansion to predict some equation or a polynomial which includes cosine function, as you can see over here.